So in this problem, I'm going to look at problem 42 from chapter 22. So 42. So here they are telling you that we have a conducting sphere, and in this solid conducting sphere, they gave out two little spherical regions, two cavities, and they tell you that the radius of this original sphere is R0, and the radii of these are R1 and R2. And on top of that, they actually introduce some charges inside these cavities, Q1 and Q2. And then they're asking us to determine the resultant electric field, magnitude and direction at locations outside the solid sphere. Okay, so what's the electric field, location and direction for R larger than R0? Now apparently there is a lot missing in this problem, right? First of all, they're not telling you the location of these cavities, and they're not telling you the location of the charges inside the cavities. Okay? But it turns out that the answer actually does not depend on these. Now what would happen here is that this is a solid conducting sphere, so all of that forms an equipotential surface, well, in this case some bulk, and we gave out some cavities and we introduced some charges inside. Now because of these charges, there's going to be some charge induced in the inner surface of these cavities. Right now, how much? Well, this Q1 is going to lead to an induction of charge of minus Q1 on the inner surface of this cavity, and this one is going to induce a charge of minus Q2 in the inner surface of the cavity. Now, because we have minus Q1 and minus Q2 that's somehow coming from the bulk of this conductor, then that must leave some additional excess charge of Q1 plus Q2, and that excess charge must go to the surface. Okay? Because in a conductor, this is a solid conducting sphere, in a conductor, all the excess charge must lie on the surfaces. So the inner part of these, the charge on the inner surface of these cavities are determined, and so we need to put all the remaining excess charge on the outer surface. Now, how will these charges distribute themselves? Right, that's one question, because we are trying to determine the electric field that will depend on the distribution of charges. Now, these are not going to be spherically symmetric, right, because this Q1 is not at the center, at least not according to the figure given there. So the electric field is not going to be spherically symmetric inside this cavity. So the charge distribution is not going to be spherically symmetric either. Same for this one. Now, what about these? Now, our problem on the face of it is not spherically symmetric. Right? So do you expect these charges to be distributed spherically symmetric? The answer is yes. The thing is, the field produced by these excess charge inside the cavity and the point charge that's lying within the cavity, they lead to no electric field inside the conductor. Right? This is in fact why we have exactly minus Q1 here and minus Q2 here. So these charges do not apply any force on the excess charge on the surface. The only force those charges feel is from themselves, right? And the way they will distribute themselves under these circumstances is going to be spherically symmetric. So even though the problem itself is not spherically symmetric, strictly speaking, the charge distribution on the outer surface is going to be spherically symmetric, and that is the only one, that is the only factor that is going to determine the electric field. Right? So this spherically symmetric charge distribution is going to act like a point charge, and the electric field strength is going to be Q1 plus Q2 divided by 4 pi epsilon naught R square if R is larger than R0. Okay? And if Q1 and Q2, so they're asking for both the magnitude and direction, so if Q1 and Q2, Q1 plus Q2, sorry, is larger than 0, then this is radially outward. And if it's less than 0, then this is going to be radially inward. Okay? So even though our problem is not spherically symmetric, because the only thing that determines the outside electric field are these charges, this is just shielded by this conductor, and that charge distribution is spherically symmetric, we can come to the conclusion that the electric field should have this magnitude. So that's all.